Hello there, and welcome to the Sleepless Scientist, a quiet corner of the cosmos where thoughts can unwind and knowledge settles gently, like dust floating in a sunbeam. Tonight, we'll take a slow and unhurried journey into time itself, not the time marked by clocks and calendars, but the deeper, quieter time woven into the structure of the universe. A time that stretches, bends, hesitates, and occasionally behaves so strangely that even the most careful scientists sit back and whisper, "This can't be right." Can it? Before we drift into this exploration, if you find these calm wanderings comforting, I'd be grateful if you'd take a moment to like this video or subscribe, only if it feels right. And if you'd like, leave a comment telling me where in the world you're listening from and what the time is for you right now. It's always a small wonder to see how many places gather together in these quiet nights, each of us in our own little pocket of the universe, yet somehow sharing the same moment. So feel free to dim the lights around you, maybe let a soft hum from a fan fill the room, and settle into whatever makes you comfortable. Tonight we'll wander through the idea that time, this thing we trust so deeply, may not be what we think it is. And if at any point your mind drifts away, that's perfectly fine. Let it drift. We'll still be here, gently unfolding the story. As the night settles around us, let's begin with a simple thought. Perhaps time is far less rigid than it seems. For most of your life, time has probably felt like one of the most reliable companions you know. It arrives steadily, second after second, never stumbling, never rushing, never pausing to catch its breath. Morning arrives after night, and night after morning, with a discipline that feels almost comforting. You wake, you work, you rest. And somewhere between all of those, time seems to quietly keep the score. Because of this familiarity, it's easy to imagine time as something universal, a kind of cosmic rhythm that everything follows. People often picture it as a straight line stretching in one direction, with all of us walking along it together at exactly the same pace. 1 second for me, 1 second for you. 1 hour for Earth, 1 hour for Mars, a shared agreement across the cosmos. But if you look closely, even for a moment, that agreement begins to fall apart. The first cracks appear when we realise that what we call now is far slipperier than it looks. You aren't actually seeing anything in real time. Light, the messenger that brings the world to your eyes, needs a moment to travel from whatever you're looking at to where you stand. Even the screen in front of you is showing you its past and not its present. That delay is so small that your mind smooths it out, blending the world into a seamless story. But the truth is still there. The present is always a little bit old by the time you receive it. Once you accept this tiny delay, it becomes easier to imagine larger ones. If the screen takes a sliver of a moment to reach you, what about a tree 100 meters away? Or the moon? Or a distant star whose light began its journey before humans existed? The night sky is a museum of ancient messages. Every star you see has already changed. Some may no longer exist. And yet, they shine above you, as if time hasn't touched them at all. It's an illusion your brain quietly accepts. But even this isn't the deepest lie our intuition tells us. Your sense of a universal now is a convenience, not a truth. Two people moving differently, one sitting still, one speeding in a spacecraft, will not agree on what events happen at the same moment. Their lines of now tilt relative to each other, like two rulers held at different angles. What feels simultaneous to one person may not be simultaneous to another. The universe allows each observer to carve their own slice of time. Imagine holding a stack of papers representing all moments that exist, past, present, future. A person who's standing still cuts the stack straight across in a clean horizontal slice, but someone rushing past carves through the same stack at a slant, slicing through different moments. Both believe their slice is the present, both feel equally certain, and both are correct. Time does not gift us a single shared moment. It gives us many, each one personal, shaped by motion. Even more surprising is the idea that time and space aren't separate things at all. They blend into one fabric, spacetime, and this fabric bends whenever matter or energy is present. That bending affects the flow of time. A clock near something massive ticks a little slower, not because its gears are heavy or tired, but because time itself is stretched thin around weight. Standing closer to the ground means standing closer to Earth's mass, and so your toes experience time ever so slightly differently from your head. The difference is unbelievably small. Fractions of a heartbeat spread across a lifetime, but it exists. An instrument sensitive enough can measure it. If time were truly absolute, gravity should not touch it. If time were truly universal, motion should not distort it. And yet both do. Time bends to the world, and the world bends time in return. All of this reveals a quiet truth. The steadiness of time is a story we tell ourselves because it's practical. It keeps our days organised and our minds centred. But underneath that story lies something far stranger. Time is flexible, personal, responsive. The way you move, where you stand, how close you are to a massive object, everything shapes the flow of your seconds. In the deep physical sense, you and I are not walking along a shared timeline. Each of us is gliding through our own stretch of time, carved by our motion and our surroundings. Sometimes those timelines align closely, sometimes they drift apart, sometimes they tilt at angles we never imagine. And as you sit here, listening, perhaps you can feel a softness in that idea, a gentle loosening of something we often grip too tightly. Time is not a ruler. It's not a ticking metronome. It's a field, a texture, a direction woven into the universe, responding to motion and gravity just as fabric responds to weight and wind. If the idea feels unfamiliar, that's perfectly fine. Let it settle quietly, like a feather drifting through the dim air of a quiet room. We'll move gently from here, letting the universe show us how time truly behaves once we invite it to shed its familiar mask. Light has always felt like one of the most obedient things in the universe. You flick on a lamp and there it is, instant, bright, unquestioning. It slips through windows, softens the edges of a room, glints off quiet surfaces, and settles gently across your hands as if nothing could ever interrupt its path. But beneath that calm familiarity lies a far stranger story. Light is not simply fast, it is the limit of fastness itself, woven so deeply into the structure of space-time that everything, your heartbeat, the movement of planets, even the flow of time, bends in order to keep its pace steady. Tonight, we'll follow light a little more closely and discover how its unchanging speed reveals the first deep fractures in our everyday idea of time. Imagine for a moment that you're standing on a quiet country road at dusk. The air is still, the world is hushed, and the last rays of the sun stretch across the fields. If a car approached you at high speed, you'd see its headlights become slightly bluer, just a touch, hardly enough for your eyes to notice. That shifting colour is called the Doppler effect, and it happens because the waves of light coming toward you are being squeezed like ripples pushed forward by a boat. But this gentle shift is only the beginning of something far more dramatic. Now imagine that you could travel not at highway speed, but at a speed so immense, so close to light itself, that the normal colours of the world begin to collapse and reassemble in front of your eyes. In this state, the warm reds that usually blur into the infrared suddenly slide back into the visible spectrum, glowing like embers waking at the edge of your vision. Hidden heat reveals itself, shadows whisper their warmth, and at the same time, ultraviolet light, normally too sharp for your eyes, falls downward into visibility, painting the world with a pale, ghostly blue. The universe becomes richer, brighter, stranger, as if someone had expanded your senses without asking. This change isn't magic. It happens because at near light speeds the wavelengths of light shift dramatically. Light ahead of you is compressed into shorter wavelengths. Light behind you is stretched into longer ones. Even though your eyes aren't designed for these transformations, the universe does not wait for our biology to catch up. It simply shifts the palette around you, and suddenly the invisible becomes visible. But there's another effect waiting quietly beside it, something called the searchlight effect. If you begin travelling extremely fast toward a landscape filled with sunlight, the world in front of you will start to brighten, not because the sun grows stronger, but because more and more photons, the tiny packets of light, rush into your eyes with each passing moment. Behind you, the opposite happens. The world fades, not into darkness exactly, but into a kind of dimming where fewer photons arrive. It's as though the universe is gently turning your attention forward, guiding your gaze like a hand placed quietly on your shoulder. And yet, even with all these changes, your senses will tell you a lie. It will feel like you're speeding up. Even if your speed is steady, even if nothing has changed in your engines or in your stride, the world ahead begins to draw near much faster than it should. This illusion happens because time itself starts to slow down for you. Not dramatically at first, just a soft drift, like the slowdown you feel when you're sleepy, and the world seems to take an extra second to reach you. But the faster you go, the more your own personal time stretches, until your seconds slip by more slowly than everyone else's. Ideas like 1 second and 1 meter begin to unspool, loosening their once rigid definitions. Distance shrinks in the direction of your motion. Time broadens. Space and time lean toward each other, as if sharing a quiet conversation. You could travel for what feels like a single year, deep in your spacecraft, only to return and discover that a decade has passed on Earth. Your journey was normal to you. Your meals, your thoughts, your heartbeat, all moving at their usual pace. But to everyone you left behind, your time flowed differently. This isn't science fiction. It's a real consequence of approaching the speed of light, and it has been verified again and again by experiments with atomic clocks flown on aircraft. The clocks that travelled, though they moved far more slowly than any spacecraft, still drifted out of sync with the ones left on the ground. Only by gently adjusting for these differences can we keep technologies like GPS aligned with the planet beneath them. As you move faster and faster, another strange thing begins to happen. Your field of view stretches and warps. Imagine playing a video game with lag, where the world you see is always a fraction behind your actual position. In the real universe, light also needs time to reach your eyes, and near light speed, that delay becomes noticeable. The world doesn't appear where it is, it appears where it was. If you turn, the universe seems to hesitate before updating its picture for you. It's like trying to navigate through a memory of the world rather than the world itself. But this delay also has a surprising side effect. Because you're seeing so many past moments of objects around you, your field of view widens. You can see more to the sides than you normally could, as though the universe is bending its edges gently inward. The stars around you gather closer. Distant lights lean toward you. Navigation becomes delicate, almost dreamlike. It's a reminder that the world we see is always slightly outdated, a stitched-together echo of the true universe that sits just beyond our reach. And when you travel fast enough, the delay no longer hides itself. The illusion of a smooth, synchronized world begins to crumble, revealing the deeper architecture beneath. A universe that refuses to give every observer the same experience of light, motion, or time. All these effects, color shifting, brightening ahead, dimming behind, the feeling of speeding up, the stretching of your vision, are not tricks or distortions. They are the universe telling you that time is flexible, shapeable, personal. They show that your now is not the same as anyone else's. They are the first cracks in the idea that time is absolute, the first hints that something deeper is at play. And once you see those cracks, once you feel the world bending around the steady heartbeat of light, you cannot unsee them. You begin to sense that time isn't a rigid ruler cutting the universe into equal slices. It's more like a fabric being tugged gently by motion, stretched by gravity, curved by speed, soft, supple, forever adjusting. These are only the first steps. Light has much more to reveal about the secret shape of time. There is a peculiar feeling that comes from moving through a world where light cannot quite keep up with you. In everyday life, the speed of light is so astonishingly fast that it behaves like an instant messenger. It delivers the shape of a room, the tilt of a tree, the sparkle of a distant street lamp, all without any noticeable delay. You turn your head, and the world turns with you. You stretch out your hand, and the light outlining your fingers seems to trace them in real time. It creates the impression that vision is perfectly synchronized with reality. But this, like so many things in physics, is a comforting illusion, one that falls apart the moment you begin to move fast enough. A surprisingly good way to understand this comes from a simple, playful experiment. A small game developed by researchers at MIT called a slower speed of light. Instead of making your character walk faster, the game gradually slows the speed at which light itself travels. You walk the same steady pace the entire time, but the universe around you begins to sag and ripple as light struggles to keep up. What begins as a gentle strangeness slowly unfolds into a complete rearrangement of how the world appears. One of the first things you notice is a kind of lag, a soft delay in how the surroundings respond to your movement. When you turn, the world seems reluctant to follow. That hesitation doesn't come from clumsiness or slow rendering. It comes from the fact that light needs more time to carry information from the world into your eyes. Every object you see is always in its yesterday, its tiny and immediate past, and normally you never notice because light is practically instantaneous. But when light slows, that hidden memory becomes visible. You steer, and the world reveals itself only after a breath. You begin to walk not through space, but through delayed impressions of space. If you try to turn right around a corner, you soon realize that the corner you see is not exactly where the corner is. You must adjust your movements earlier. You must anticipate. You begin to navigate not the world itself, but its lingering shadow, its echo. The experience resembles playing a game with heavy network lag, where your actions occur before the world has updated its information. Except here, the network is the fabric of light itself, the quiet envelope that carries reality toward your senses. As the speed of light falls further in the game, another transformation begins. Your field of view starts to stretch, not like a digital effect or distortion on a screen, but like a natural widening of perception, almost as if the world is gently opening itself. Because you're seeing objects as they were at many slightly different moments, your mind blends those moments together into a larger field. Objects that were originally at your periphery lean inward. Patterns that were once hidden behind you creep into sight. You begin to see more of the world at once than you ever could in ordinary life. The universe becomes panoramic, as though it's inviting you to witness its full breadth. And then there's the sense of speeding up, even though your walking pace never changes. The world flows toward you more quickly, not because you've increased your speed, but because your own time is quietly stretching. Imagine walking along a familiar path, one you know by heart, the distance between lampposts, the rhythm of your footsteps, the softness of the night air. Now imagine that with every step the path seems shorter, as though space itself is gently folding inward. You arrive sooner, not because you're moving faster, but because the universe has adjusted the meaning of sooner. This feeling of unexpected acceleration is one of the softest yet strangest hints that time can bend. Your heart still beats the same, your thoughts unfold at their usual pace, If someone stood beside you inside this slowed light world, they'd feel normal too. But someone watching from outside, someone whose world still holds light at its true speed, would see you moving differently. They would see your seconds and their seconds drifting apart like two boats gently separating on a lake. As these effects accumulate, the world begins to feel almost like a memory of itself. Trees shimmer where they shouldn't. Buildings lean at unusual angles. Shadows bloom wider. Colours begin to stretch across your vision as light strains to keep pace with your motion. Each photon carries a sliver of the world's past, and when you walk quickly enough through that delayed information, something remarkable happens. The world shows you multiple pasts simultaneously. This overlapping of past moments creates the illusion of a wider field of view, as if the universe quietly borrows from its own history to fill in the present. The shift isn't sharp or unsettling, it's soft, a gentle blending. Light does not announce these changes, it simply allows your vision to widen, like curtains being slowly pulled apart. And there is something almost dreamlike in the idea that you could outrun the immediacy of your own sight. We spend our lives assuming that vision is direct, that what we see is what is. Yet the truth is quieter and more fragile. Vision is always late. Light must travel before we can know anything. When you move fast enough, that travel time grows just long enough to reveal the machinery beneath the illusion. You begin to see the world as it truly is. Not a seamless, immediate picture, but a mosaic assembled from tiny slices of time. Every tree, every wall, every stone, every reflection. Each exists in your eyes as a collection of delays, and when those delays begin to widen, the mosaic reveals its seams. This realization changes something fundamental. It invites you to step back and ask, what is now, if the world can only reach you after a moment has passed? What is here, if your senses are always catching up? And if light, the universe's messenger, can be tugged and stretched and slowed, then perhaps time, the stage upon which all things unfold, is not the straight, steady line we once believed, but a soft, malleable fabric. All of these gentle distortions, steering lag, stretching edges, the illusion of acceleration, the widening of vision, are not glitches or tricks. They are glimpses of the deeper truth that the universe has always held. Motion reshapes the world, and time bends quietly behind every step we take. And from these hints, a larger picture begins to emerge, one in which gravity, speed, and the very structure of spacetime whisper the same message. The universe is far more flexible than our senses ever reveal. If you place a clock on your bedside table and another one on the windowsill above it, you might imagine the two ticking together in perfect harmony. After all, they share the same room, the same air, the same quiet moment of your life. And yet, despite every similarity, the one nearer to the floor, closer to the centre of Earth's gravity, ticks a little more slowly. Not enough for your ears to notice, not enough for the shadow of a second hand to reveal the difference, but enough that, if you watched both clocks with instruments sensitive enough to track the tiniest ripples in time, you would find the lower one falling, behind. This soft stretching of seconds is one of the first hints that gravity is not simply a downward pull. It is something deeper and more delicate, a bending of the world itself, a reshaping of the fabric that time flows through. The stronger the gravity, the slower time moves. This idea sounds almost poetic, yet it is one of the most confirmed truths in physics. And although the effect is small on Earth, it is everywhere around us, quietly influencing each moment. To imagine how this works, picture time as a gentle stream flowing across a landscape. In places where the ground dips downward, the water slows, pooling slightly before continuing its journey. In places where the earth rises, the water rushes more freely. Gravity creates these dips, these subtle basins, shaping the flow of time the way the contours of a valley shape the movement of a river. Your clock, your heartbeat, your thoughts, all move through that stream, drifting slower where gravity deepens the ground beneath you. Scientists tested this idea on Earth using one of the most elegant experiments of the 20th century. On the roof of a tall building, they released a beam of light downward into a detector placed far below. If gravity truly slowed time near the ground, the light should gain energy as it fell, its peaks bunching together, its rhythm tightening slightly, the way cars squeeze into a bottleneck when a road narrows ahead. This effect, known as gravitational redshift when light moves upward, and gravitational blue shift when it falls downward, is tiny on Earth. Yet when the detector listened closely, it heard the change. Light had truly quickened its beat on the way down, confirming that time itself flowed more slowly below. This slowing of time isn't limited to dramatic experiments. Your entire body experiences it every day. Your feet are closer to Earth's mass, so the seconds flowing through them drift a tiny bit slower. Your head, floating slightly farther from the centre of the planet, experiences faster time. The difference is unbelievably small. Spread across a lifetime, it amounts to less than the blink of an eye. But the universe makes no exceptions. Time bends for everyone, everywhere, whether we're aware of it or not. Even our technology depends on acknowledging this softness in time. Above us, GPS satellites orbit Earth, drifting through weaker gravity, where time flows a little faster. Their clocks gain extra microseconds each day. If we didn't adjust for that gentle difference, your navigation app would be wrong by entire city blocks. Every direction you receive, every turn-by-turn guide through familiar streets, is only accurate because we account for the way gravity shapes time. Your phone works because the universe refuses to let time be uniform. It's tempting to think gravity slows time only near planets or stars, but the truth is broader. Any mass, any energy, pulls at the fabric of space-time, bending it, reshaping it, affecting the rhythm of seconds. Even a mountain near you slows time around its base ever so slightly. Even your own body bends space-time, creating a tiny, almost imperceptible dip in the flow of moments. But Earth's influence is just the beginning. Consider how the sun pulls at the fabric of the solar system. We live inside a vast bowl of its gravitational shape, and the flow of time here is slower than it would be in deep space where gravity is weaker. For every minute that passes in a region free of gravity, one untouched by any heavy object, we experience only slightly less. It's as though standing near the sun places us in the shallow end of a cosmic pool, where seconds drift with a thicker, heavier sway. If you travelled closer to the sun, to a planet like Mercury, the effect would deepen. The sun's pull there is stronger, carving a deeper well in the structure of space-time. Time would slide more slowly across its surface, softening each second by the tiniest amount. A full human lifetime spent on Mercury would leave you only a few dozen seconds younger, relative to someone who lived far from all stars and planets. It's hardly enough to matter in ordinary life, yet it carries a profound message. Time is not universal. It bends and adapts to its surroundings like soft cloth shaped by weight. These differences are small here in our solar system, but they reveal a truth that becomes powerful as we move toward heavier objects. The deeper the gravity, the slower the time. Near a neutron star, seconds would ooze like cold honey. Near a black hole, time could stretch so thin that it nearly stops. And yet everything you feel, your heartbeat, your breath, the flow of your thoughts, would still seem perfectly normal to you. You would only notice the strangeness when you realize that the universe outside your gravity-warped bubble had raced far ahead. On Earth, these distortions are gentle, almost tender. They whisper more than they shout. But they show that our comfortable idea of time, steady, universal, absolute, is only an approximation, a story we tell ourselves because it makes life easier. Underneath that story lies a deeper truth. Time is not a single river. It is a network of streams, each flowing at its own pace, shaped by the mass and energy around it. Every mountain, every planet, every star, and even you contribute to the shaping of time's terrain. Each step you take on Earth carries you through subtly different rhythms of seconds, and the universe honours those differences with exquisite precision. To notice this is to understand that time is not a static backdrop. It is alive, responsive, sculpted by gravity's quiet touch. What feels like a single, continuous flow becomes, under close examination, an intricate tapestry of shifting tempos. And once you see that, once you recognise how easily gravity can stretch or soften a second, the world begins to feel different. Softer, less mechanical, more like something alive, something that moves with you rather than ahead of you. If you were to step outside on a quiet morning and look up at the sky, you might imagine that everyone on Earth is sharing the same moment. A person drinking tea in London, another walking along a beach in Vietnam, someone preparing breakfast in Brazil, all of them drifting through the same second, the same minute, as though time were a single blanket wrapped gently around the entire planet. It's a comforting thought, and in daily life nothing seems to contradict it. But underneath that shared feeling lies a deeper, softer truth. The flow of time on Earth is not even the same from top to bottom, let alone from one world to another. The differences are tiny here, small enough that we can ignore them without consequence. But they contain a lesson that grows more dramatic as we wander outward into the solar system. A lesson about how gravity shapes every heartbeat, every breath, every moment we experience. To begin this quiet exploration, imagine two clocks. One sits on your nightstand, the other sits on the roof of your home. They look identical, tick identically, and were built from the same small pieces of metal and quartz. But the one on the ground floor rests deeper in Earth's gravity, and the one on the roof sits slightly higher in a region where the planet's pull is just a little weaker. Because of this, the lower clock runs more slowly, not by minutes, not by seconds, by an amount so small that a lifetime would reveal only the faintest hint of drift. But the difference is real. Earth's gravity gently stretches time near its surface like a hand tugging at a soft fabric. If we zoom out further, gently lifting ourselves away from Earth's ground and into the stillness of space, the effect grows stronger. A clock that floats far above the planet, untouched by its weight, experiences time more freely. Every minute inside that calmer region of gravity passes slightly faster than it does on Earth. This is not a flaw or a trick. It's the universe's natural rhythm, a rhythm that satellites rely on every moment of every day. The navigation systems guiding airplanes and phones and ships depend on tiny corrections to account for this difference. Time above Earth simply moves differently than time below. It's a quiet, cosmic negotiation that keeps our technology from drifting into confusion. Without these corrections, your navigation app might place you in the wrong street or the wrong city. The world of technology keeps time so precisely only because it recognises that gravity bends it. But Earth is not the only shape that carves time. Above us stands the Sun, a vast glowing sphere whose presence dominates the entire solar system. Its gravity is enormous, deep enough to pull 8 planets, dozens of moons, and countless smaller bodies into orbit. And because of that immense pull, the Sun slows time throughout the region around it. If we imagine a region far from every star, an empty place where gravity fades to nearly nothing, we can think of it as the universe's baseline for time. In that distant, untouched region, a minute of time flows almost purely, without being shaped by the weight of any nearby celestial body. But here near Earth, inside the Sun's gravitational influence, that minute becomes just a little shorter. Our seconds stretch ever so slightly, softened by the Sun's presence. Over an entire human lifetime, the difference adds up to several heartbeats worth of time. Not enough to change your life, but enough to show how precisely the universe keeps track of its rules. Imagine two people, one who lives far away from all stars drifting in deep space, and another who lives on Earth. After 70 or 80 years, the person on Earth would emerge just a few dozen seconds younger, simply because time ran more slowly here. This difference is gentle, almost invisible, but deeply real. Now imagine travelling even closer to the Sun, to a planet like Mercury. There, the Sun's pull is far stronger. Standing on Mercury feels like standing deep inside a cosmic well, a steep, heavy basin carved out of space-time itself. Time flows more slowly on Mercury than on Earth, just as time on Earth flows more slowly than in deep space. But even here, the difference is delicate. A whole lifetime on Mercury would only leave you a handful of seconds younger relative to someone who lived very far from the Sun and its influence. The change is not dramatic enough to grant anyone additional years, but it is enough to reveal a pattern. Time, it seems, is not a single river flowing steadily from past to future. It is more like a network of tiny streams, each flowing at its own pace, shaped by the surrounding landscape of gravity. Where the landscape dips, near a planet, near a star, time slows. Where the landscape rises, far out in space, time speeds ahead. And each world in our solar system experiences its own tempo. You might expect that travelling to Mercury would let you gain more time, the way one might gain altitude. But the benefits are slight, and the costs steep. Mercury's surface is harsh, its sunlight overwhelming, its days unbearably long. For the small handful of seconds you might save over a lifetime by living closer to the Sun, you would endure a world where temperatures swing wildly, where radiation rains freely, and where the sky burns with relentless brilliance. Time may drift more slowly there, but comfort does not. And yet the comparison between Earth, the Sun, and Mercury reveals a quiet, universal truth. Time is shaped by gravity, everywhere, without exception. Every mass in the universe, from tiny asteroids to colossal stars, bends the flow of seconds around it. Your own body, small as it may be in cosmic terms, tugs ever so lightly at the fabric of space-time, forming a tiny dimple of slower time around your heartbeat. This idea, once absorbed, has a way of softening the world. It invites you to imagine time not as a rigid sequence of events, but as a gentle fabric that stretches and shrinks depending on where you stand. It whispers that even the seconds flowing through your life are part of a larger living landscape shaped by invisible curves and unseen weights. It reminds you that the universe is not a machine with a single, universal clock, but a collection of different rhythms, each one shaped by the quiet pull of gravity. Earth's rhythm differs from Mercury's. Mercury's differs from that of deep space, and your own rhythm is subtly different from the rhythm just a few feet above your head. When seen this way, time becomes less like a strict guardian marching forward and more like a soft companion, adjusting its stride to match the universe around it. And in that softness lies the first glimpse of a larger truth, the idea that time is not fixed, not absolute, but deeply connected to the shape and weight of the cosmos. If you were to drift far above our solar system, beyond the planets, beyond the comets, beyond the soft glow of scattered dust, you would eventually feel gravity's grip loosen around you. Out there, time flows more freely, like a river unburdened by stones. But if you continued your journey toward the heart of a galaxy, toward the place where starlight bends and gas spirals inward like waters down a drain, you would encounter something far stranger. A region where time slows so dramatically that seconds nearly lose their meaning. A region shaped by objects so massive, so concentrated, that they deform the universe in ways almost impossible to imagine. These objects are supermassive black holes, the quiet giants resting at the centres of galaxies. Our own galaxy, the Milky Way, shelters one roughly 4 million times heavier than our Sun. Others in distant galaxies are far larger, reaching tens of millions or even billions of solar masses. And yet, despite their terrifying size, they often sit in darkness, hidden behind swirling clouds of gas and dust, whispering through gravity alone. To understand how such a thing affects time, imagine spacetime as an elastic sheet stretched tight. Every object leaves a slight indentation on this sheet. A small stone creates barely a dimple. A planet creates a deeper one. A star creates a well, but a black hole, a supermassive one, forms a chasm so steep that, near its edges, even time begins to slip. If you drifted towards such a place, your experience of time would begin to change long before you reached anything dangerous. Imagine a spaceship approaching the boundary of a supermassive black hole, its engines humming softly in the vacuum. Inside the ship, your heartbeat feels normal, your breathing feels normal. The ship's clock ticks steadily. You feel no pressure, no slowing, no stretching of minutes. Everything seems perfectly ordinary, and yet to an observer far away, someone watching, through a distant telescope, you're already slowing down. This is one of the most profound truths in relativity. Time flows differently depending on where you are and how strong gravity is around you. Near a supermassive black hole, gravity is so intense that it stretches time like warm taffy. Your moments extend, your seconds lengthen. To someone watching from afar, each movement of your hand, each blink of your eyes, would appear to take longer and longer. If you waved, they might see your arm rise over the course of hours. If you breathed, they might see the inhale stretch across days. But inside your own experience, nothing strange is happening. You are simply drifting, floating in a quiet sea of warped space, unaware that you're slipping into a nearly frozen time. Now imagine hovering near the event horizon, the boundary where escape becomes impossible, where the inward pull of space-time becomes deeper than any motion outward could resist. You aren't crossing it, only resting near it, like standing at the edge of a cliff and peering down into a fog you cannot see through. Here, the effect becomes even more dramatic. If you spent 30 minutes near this boundary in your own time, just half an hour, long enough to make tea or read a few pages of a book, hundreds of years might pass in the outside universe. The world you left behind would rush forward without you, aging rapidly in a way you could never witness unless you returned. Friends, cities, entire generations could rise and fall while you experienced only the passing of a simple afternoon. And if you pulled away, if your ship ignited its engines and climbed back into calmer gravity, you would watch the universe blossom with new centuries. The stars themselves would appear subtly repositioned. Signals from Earth would arrive containing voices and messages from people who had not yet been born when you left. You would have skipped across time not by moving fast, but by lingering near a place where gravity stretched your seconds thin. The beauty of relativity is that it does not care about intent. It only cares about motion and gravity. For you, the experience would feel peaceful, almost serene. But for someone watching from afar, it would resemble witnessing a candle flame slow into a long, unbroken glow. To them, your fall toward the event horizon would appear to take forever. They would see you slow more and more, fading into near stillness at the boundary, never quite crossing, never quite disappearing. Light from your ship would stretch into deeper and deeper reds until it dimmed beyond perception. It would look as though you had frozen in place, captured in an eternal moment. But from your perspective, if you allowed yourself to drift inward, you would cross that boundary in a heartbeat. Softly, silently, without any sign that you'd stepped somewhere extraordinary. Time inside behaves differently. There is no flashing sign that says, beyond this point, seconds behave strangely. You would not feel the bending of time, you would simply live it. Of course, the interior of a black hole is a place our physics cannot yet fully describe. It is a region where our understanding blurs into speculation, where equations falter, and where the familiar structure of space-time might cease to exist. Yet the part we do understand, the region just outside the boundary, is already remarkable enough. It shows us the most dramatic demonstration of gravitational time dilation that the universe offers. In the presence of a mass so concentrated, time becomes malleable to an extreme degree. What flows gently on Earth becomes syrup thick near a black hole. What feels natural to you becomes stretched thin to observers far away. The difference is not metaphorical, it is woven into the mathematics of space-time itself. But we don't need those equations to appreciate the wonder of it. It's enough to imagine a place where time slows so fully that it becomes almost still. Standing near such a cosmic shoreline would be like placing your hand onto a waterfall of distorted moments, watching the flow of time pool around your fingers, and in that stillness you would understand more deeply than ever before that time is not an absolute universal current. It is a local experience, shaped by the weight of the world beneath you. The universe tells its stories in seconds, but not all seconds are equal. Some pass quickly, some pass slowly. And near the silent giants at the centre of galaxies, time nearly forgets how to flow at all. For most of your life, the idea of dimensions has probably felt like something simple, almost mundane. You wake up in a familiar room, reach toward the lamp beside you, step out of bed, turn left, turn right. You move without thinking through length, width, and height. These three directions, forward and back, side to side, up and down, are so deeply woven into experience that they feel like the only natural structure space could possibly have. They are the quiet background of every moment you've ever lived. But tonight let's slow down the idea of dimensions, as though we're setting them gently on a table to observe their shapes. When we do, something surprising begins to appear. The sense that the world might be hiding an extra direction, one we move through constantly without ever seeing. To begin, picture a single line, a one-dimensional world. In this world, a tiny being that lives along the line can only move forward or backward. Nothing else exists for them. They cannot step sideways because sideways has no meaning yet. Their entire universe is a string stretched taut. Now imagine expanding that line into a flat surface, a two-dimensional world like a sheet of paper. Suddenly there are new possibilities. You can walk left or right, but also forward or back. You can explore an entire plane of existence. A being that lives here, let's call them Lynn, might believe their world is complete. But if you reached in from above and touched the page with a fingertip, Lynn would see only a circular outline appear. They would never see the full shape of your finger or understand that your body exists in a direction they cannot experience. To them, you would be a shifting pattern, a moving boundary that seems to appear from nowhere. And now imagine stepping out of that sheet into the three-dimensional world we know. Height appears. Suddenly you can reach upward and downward. You can lift a cup off a table, step onto a chair, climb a hill. You move not just across a surface, but through space that has depth. A being trapped in two dimensions would never guess how effortlessly we pass through this added direction, how natural it feels to rise above the plane of their existence. But here is the quiet, astonishing thought. What if we are just like Lynn? What if the three dimensions we call home are not the whole story, but only the slice we can see? And what if time, the steady sequence of moments we move through, really is another direction, hidden from our eyes the way height is hidden from a two-dimensional being? It sounds strange at first, but notice something. You are always moving through time. You have no choice in the matter. Even when you lie still, your seconds flow forward, carrying you from one moment to the next. It is as if some gentle wind is pushing you along an invisible path. You cannot pause this motion. You cannot step backward. You cannot leave the path entirely. You drift along it constantly, without effort and without control. This is not how ordinary dimensions behave. If you want to move forward or backward, you can. If you want to stay perfectly still, you can. But time doesn't offer that choice. You're always travelling through it, even when everything else seems still. This unending movement suggests that time has a direction in the same way space has directions, except that, unlike space, we cannot see that axis directly. To sense it, try imagining the world from a distance, not as a movie unfolding frame by frame, but as a structure that already contains all its moments. Imagine compressing all 3 dimensions of space into a thin sheet, like a map laid flat. Now imagine stacking many such sheets on top of one another, each one representing a different moment. The past rests beneath you, layer after layer. The future rises above you, a tall stack waiting to be reached. And your life, the part you experience as now, is simply the slice your consciousness currently occupies. If you were a being unable to see this vertical stack, you would believe that time flows. But from the deeper perspective, nothing flows. You're merely passing through successive layers, guided by a gentle upward drift of existence. Just as a 2-dimensional creature cannot see height, but is still affected by it, we cannot see time but are carried by it. This view does not imply destiny or fate. It only suggests that time, like space, might be part of a larger structure. And in this structure, every event, your birth, your childhood memories, the conversations you haven't had yet, may have a kind of quiet place in the stack. But if time is a dimension, why don't you feel its shape? Why can't we step sideways into a different moment the way we can step sideways in a room? The answer lies in how thinly we extend along the time axis. In space, you occupy a volume. You are tall, wide, and deep. You have thickness. But in time, you exist only as a sliver, a momentary presence. You do not stretch across minutes or hours or years. You experience them one by one, always living at the narrow edge of your own timeline, never fully aware of how far it extends behind or ahead of you. A being in 2 dimensions cannot see the full height of a 3-dimensional object. They cannot understand that the circle on the page is merely the cross-section of a sphere passing through. In the same way, we cannot see our full extent in time. We only see the present, our own cross-section, while the rest remains hidden. This is not a limitation of our senses, but a property of how time behaves. Once you think this way, the world begins to feel different. Moving through your day becomes less like walking along a path, and more like drifting upward through layers of a 4-dimensional world. Your memories are not left behind. They sit on the layers beneath you. Your future is not a blank waiting to be written. It is a region of the stack you have not yet reached. And all of this builds toward a deeper insight. That time, the very thing we treat as linear and absolute, might simply be one more direction in a universe far larger than our senses can grasp. If you were to sit quietly for a moment, truly quietly, without movement, without distraction, you might feel as though you've stopped. Your body rests, your hands lie still, your breath softens, and everything within you seems to settle. Yet even in that perfect stillness, you're travelling. You're moving through a dimension you can't see, can't touch, and can't step out of. A dimension as real as length, width, or height, yet hidden behind every moment of your life. This hidden direction is time. The idea may feel abstract at first, like a poetic metaphor rather than a physical truth. But the more slowly we explore it, the more tangible it becomes. So let's imagine space in the simplest way possible. Imagine flattening all of 3-dimensional reality, every room, every street, every mountain, into a single thin sheet. A 2-dimensional surface that holds all locations, but none of the depth you're used to. Now gently lift that sheet and place it upright, like a page in a book. In this view, that entire sheet represents a single moment in the universe. one slice of existence. Everything that occupies that moment, every breath, every whisper of wind, every star shining in the night sky is captured within it. But one sheet alone cannot describe a full life. So we imagine thousands of sheets, millions of them, stacked vertically in a tall column. The layer at the bottom represents a distant past. The layers in the middle hold the present, and the layers above represent moments you have not yet reached. You're not stretched across these layers. You exist only in one, the one your consciousness currently occupies. But there is a subtle drift, like a gentle upward breeze, carrying you from one layer to the next. This upward drift is your passage through time. You cannot stop riding this breeze. You cannot turn around in it. You cannot step sideways to another moment. The flow is not optional. It is the quiet, natural motion of your existence. Even when your body rests and your thoughts wander, this drift continues. You move upward simply because that is how beings like us exist in a four-dimensional universe. But what determines the angle of your path? What determines how quickly you rise through the stack of moments? This is where the strange beauty of relativity enters. Imagine holding a long arrow pointing straight upward through the stack of time layers. This arrow represents your motion through time when you're not moving through space. When you sit perfectly still, your arrow points almost straight up. Almost all of your motion is carried upward, toward the future. That is why your seconds feel normal, steady, familiar. Now imagine that you begin walking. The arrow tilts slightly, leaning a bit into the surface of space. Some of your motion, just a tiny fraction, begins to spill sideways into the sheet. Because your total motion through space-time is fixed at a certain amount, any tilt into space must reduce your motion upward through time. In other words, when you move through space, you lose a little motion through time. Your personal seconds lengthen, stretch, soften. Time begins to slow for you, gently, imperceptibly. And if you move faster, much faster, this tilt grows deeper. More of your arrow slides into the sheet of space, leaving less of it pointing up. Your time slows further. To you, everything still feels normal. But to someone who remains more upright, more aligned with the vertical flow of time, your seconds appear elongated, your heartbeat slightly delayed. This is not symbolic reasoning or poetic ornamentation. It is the soft, geometric truth behind time dilation. In the extreme case, approaching the speed of light, your arrow lies almost flat against the sheet. You pour nearly all your motion into space, leaving almost none for your climb through time. And in that limit, your flow through time becomes so thin that it nearly halts. Not because your body does anything special, but because the geometry of motion through space-time demands it. Even though we are using metaphors of sheets and arrows, the underlying idea is deeply physical. Your path through the world is not just through space, but through space-time, a combined fabric where time is one more direction. And your direction through this fabric determines how quickly your moments unfold. To make this easier to feel, imagine paddling a canoe on a river. If you point your boat straight upstream, all your effort goes toward pushing against the current. But if you angle slightly to the side, some of your energy goes toward crossing the river instead of fighting the flow. You don't travel upward as quickly anymore. Part of your motion has been spent sideways. Your movement through time works the same way. Standing still on Earth is like pointing your canoe straight upward in the stack of moments. Moving through space, walking, driving, orbiting, is like angling sideways. The more you angle, the less upward progress you make per second. This idea also explains something that once puzzled generations of physicists: why nothing can move faster than light. It isn't because of some arbitrary speed limit handed down by the universe. It's because moving faster through space would require tilting your arrow so far sideways that no part of it remains pointing up. You would need to stop moving through time entirely, and beings like us simply cannot do that. In this view, light itself is not fast because it tries to be. It is fast because it has no upward component at all. It is a traveller whose motion lies entirely within the surface of space. Unlike us, it does not climb through the layers of time. It glides along the sheet, never rising, never falling. In its own strange sense, light never ages. These thoughts may feel abstract, but they reveal something intimate about the way we experience existence. Every step you take, every spin of a wheel, every orbit of a planet is a trade. A bit less motion through time, a bit more motion through space. You and the universe negotiate these trades constantly, silently, without your awareness. And the result is the shape of your seconds, the pace of your life. Once you begin to sense this, the world feels different. Walking becomes not just movement across the ground, but a gentle tilt of your arrow into the surface of space. Sitting still becomes a moment of perfect verticality, a pure drift through the river of time, and the idea of time itself changes from a strict ticking of clocks to a flowing ascent through a landscape of moments. You may never see this dimension directly, but you feel it every second of your life. It is the invisible direction that carries you from morning to night, from experience to experience, from memory to memory. And in understanding that, you glimpse the deeper structure of reality, a structure where time is not something that happens to you, but something you move through, guided by the quiet geometry of the universe. There is a story, simple yet unsettling, that has followed relativity since its earliest days. Two twins stand together in the same moment, sharing the same breath of morning air. One remains on Earth while the other boards a starbound vessel that will drift through space at extraordinary speed. The travelling twin experiences a journey that feels perfectly normal. Days filled with quiet routines, meals, long stretches of thought, long stretches of sleep. And when they return home, they expect everything on Earth to feel as if no time at all has passed. But it hasn't quite worked out that way. The twin who stayed behind has aged more. The traveller has not. Their seconds have stretched differently, even though both lived through what they believed were ordinary days. And the difference does not come from magic, or biology, or tricks of memory. It comes from geometry, soft, silent geometry stitched into the shape of space-time. To feel how this works without any symbols or complicated diagrams, imagine space-time once more as a tall stack of thin, translucent pages. Each page is one moment. The stack is tall enough to hold an entire lifetime. Standing still on Earth means your path through these pages is almost straight upward. You drift from one page to the next at a gentle, uniform pace. Tick, 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 like a slow breeze carrying you along. This is Twin A, the one who stays home. Their arrow through the world points almost straight up, rising cleanly through the layers of time. Now imagine Twin B, the traveller. When they board the starship and begin to accelerate, their path tilts. Instead of moving straight upward through the stack of moments, they slide diagonally, spending some of their motion travelling sideways through space. To us, this looks like movement across the universe, but to space-time itself it looks like a rotation, like someone gently tilting a plank as they carry it through a doorway. A tilted plank casts a shorter shadow on the floor than a vertical one. In the same quiet way, a tilted world line casts a shorter shadow on the time axis. That shadow is the experience of aging, the number of seconds, heartbeats, thoughts, dreams. The deeper the tilt, the less upward motion you have left for time, and the fewer seconds pass for the traveller. No magic, no paradox, only geometry. If you imagine marking the stack of time pages with a thin pencil line showing the path each twin takes, you would see that Twin A's line rises almost directly upward in a long continuous stroke. Twin B's line leans at an angle, travelling through fewer layers of the stack for the same length of world line. When the traveller returns to Earth and both twins stand together again, the difference in the length of those pencil lines becomes the difference in their ages. The physical world does not care that the traveller feels as though their seconds flowed normally. Inside their own tilted path, everything does feel normal. Their heartbeat keeps its usual rhythm. Their meals arrive regularly. Their mind drifts through thoughts at what seems like a familiar speed, but that internal rhythm is not measured against Earth's, only against their own. They have tilted their arrows so deeply into space that much less of their motion was spent rising upward through the layers of time. From afar, someone watching Twinbee's journey through a powerful telescope would see their seconds lengthen, just slightly. Movements would appear to take longer. The ship's pulses of light would arrive with a softer rhythm. To the observer, Twinbee's time seems stretched thin, like a piece of warm taffy being pulled gently. But aboard the ship, everything looks completely ordinary. This perspective, seeing aging as the length of a path through space-time, softens the paradox until it dissolves. The only reason the traveller returns younger is that their path climbed fewer time layers. Their upward motion was reduced because part of their journey was spent sliding sideways through space. The same idea explains why nothing can outrun light. Light's path lies perfectly horizontal in the page stack model. It pours all of its motion into space, leaving no upward movement through time. It does not age. It does not drift. It simply lives inside the sheet of space itself, skimming along the surface of the stack without rising through it. Light is what happens when an object spends all its motion sideways. Meanwhile, we spend almost all of ours upward, experiencing time fully but moving slowly across space. The twin paradox is the middle ground, a case where a traveller borrows some of their upward climb to glide sideways, just enough to show that time is not a single universal rhythm, but a personal one shaped by the path you choose. It helps to imagine holding your hand in a beam of sunlight. That sunlight is the end of a journey that did not age the photons at all. They travelled sideways through the cosmic stack. And when you move your hand, the angle of that movement changes the path you take through time's layers. Every gesture is a tilt of your arrow. Once you see it this way, the twin paradox no longer feels like a riddle. Instead, it becomes a gentle reminder. Time is not a substance poured equally over everyone. It is the distance you climb through the tall, invisible structure of space-time, and the angle of your journey, your motion, determines how much of that climb you complete. It is a quiet truth, but once you hear it, it changes the way you think about every moment you live. If you close your eyes for a moment and imagine yourself from above, perhaps you picture your outline, the width of your shoulders, the length of your body. You imagine thickness, height, depth, the unmistakable shape of someone who occupies space. You are real in 3 dimensions. You have volume. You occupy a place in the world. But what if you imagine yourself not in space, but in space-time, in the full landscape of the universe, where time is a direction just as real as all the others? The picture becomes very different. In that deeper view, you're not thick. You're not elongated. You're not stretched along the axis of time the way you are along height or width. Instead, you are thin, astonishingly thin. You're like a coin held upright, a single shimmering slice, hovering between what has passed and what has not yet arrived. You exist in a moment so narrow that it's more fragile than a breath. The rest of your timeline, your childhood, your memories, your future, does not appear beside you. Those layers exist, but you do not stretch across them. In space, you occupy depth. In time, you occupy only an instant. That thinness is the reason we cannot see time the way we see space. You cannot turn your head and look into yesterday. You cannot lean sideways and peek into tomorrow. You do not extend through time the way a mountain extends through space. You're the tiniest of slivers in the 4th dimension, a thin cross-section of a much larger story. To understand this more fully, it helps to think again of the 2-dimensional world we met earlier. Imagine a flat, paper-thin creature living on a sheet. For them, depth does not exist. They have no awareness of what it means for something to rise above the plane. If you were to lower a sphere through their world, they would see only changing circles on their sheet. they would not know that those circles were slices of a larger shape. Now imagine that same creature turning slightly within its plane. Its outline changes, its shape flattens or shrinks depending on how it tilts. It is the same being, with the same volume in the third dimension, but from the view of the two-dimensional world it looks thinner, narrower, distorted. What they see is a projection, a shadow, of something they cannot fully imagine. We are the same. We are beings who live fully in 3 dimensions but see only a thin slice of the 4th. Our bodies do not stretch through time. We experience ourselves one moment at a time, the way a 2-dimensional creature sees only the shape of a sphere where it intersects their plane. This helps illuminate one of the strangest phenomena in physics, Lorentz contraction, the gentle shortening of objects that move at high speed. When an object travels quickly through space, its motion causes its path through space-time to tilt. And just like a long plank tilted toward the horizon casts a shorter shadow, a fast-moving object appears shorter along its direction of motion. It is not that the object really shrinks in some mechanical sense. Instead, its full 4-dimensional shape intersects your slice of reality differently. Your view of it is a projection, one that changes as the object rotates through the time dimension. Imagine watching a dancer twirl on stage. When they face you directly, you see the full width of their silhouette. As they turn sideways, the silhouette narrows. When they turn even further, they nearly vanish into a thin line. They have not changed. Your perspective has. This is what motion does in space-time. It changes how objects intersect your particular moment. Now picture yourself, not as a dancer on a stage, but as a being drifting upward through time. Every object you see, every person, every stone, every beam of light, meets you at this thin edge of your own time slice. You see only the slice, never the full shape. You witness cross-sections of existence, each one a moment shaved from a deeper whole. This idea becomes even more striking when we think about our memories. They feel stored inside us, part of who we are. Yet in space-time, those memories are not inside your present shape. They exist on layers beneath you, on earlier slices of the timeline. What you call a memory is not the past living in your mind, but your mind reaching downward through the thinness of your moment, touching echoes of slices you have already lived through. And what about your future? It does not exist beside you, waiting to be stepped into. It exists above you, in thin layers you have not yet reached, shaped by choices you have not yet made. This thinness, this cross-sectional existence, transforms how we think about time. We often imagine time as a line stretching forward and backward. But in space-time, it is more like a tall structure that we rise through slowly, always encountering only the surface of each new moment. We never see our full shape in time, just as a 2-dimensional being never sees the sphere passing through its world. We only ever experience the present, the frontier of our journey upward. Some people find this idea unsettling, as though it means we are incomplete. But the opposite is true. Our thinness in time is the reason our experiences feel vivid, immediate, delicate. It is why moments matter, because they arrive one at a time, not as a full tower, but as a soft unfolding. Think about how a single moment can feel so powerful. A joyous memory, a difficult goodbye, a quiet morning with sunlight warming the edge of your pillow. Each of these is a thin slice, but it is precisely that thinness that makes it feel meaningful. If we stretched across hours or years at once, experiences would blur. But because we are so thin in time, each second touches us finely, like the tip of a paintbrush brushing against a canvas. In this view, being thin in time is not a limitation. It is a gift. It allows us to live with a kind of fragile clarity. It lets us feel the passing of a moment as something complete, something that cannot be revisited in quite the same way. Every second is its own small slice of existence, and because we are so narrow along the time axis, we meet each slice with our full attention, full presence, full being, and with that the idea of dimensions becomes less mathematical and more profoundly human. We are creatures who extend richly through space and delicately through time, carried upward through the layers of reality by a gentle breeze we cannot see. If you've ever placed your hand in a sunbeam, you felt light arrive with a sense of effortless speed. It slips through the air, glides across dust motes, and lays itself gently across your skin, as though nothing in the universe could slow its journey. In a vacuum, in the empty spaces between stars, that's almost true. Light moves with a steadiness so perfect that it forms the quiet heartbeat of the cosmos. But the moment light enters matter, air, water, glass, its certainty begins to soften. It hesitates. It wavers. It moves more slowly. Not because it grows tired or heavy, but because it becomes entangled in a delicate dance with the atoms around it. The universe shows us here, in one of its simplest interactions, how even the purest motion can be reshaped by the fabric it travels through. To understand this gently, imagine walking through an open field on a calm day. You can move forward freely, with nothing resisting your steps. That is light in empty space. Now imagine walking through a crowded street at dusk. People brush against you. You step around them. You pause as someone crosses your path. You still move forward, but your progress is slowed by each interaction. Light, when passing through matter, experiences something similar. Inside any material, whether it's a pane of glass, a pool of water, or the small space between two air molecules, there are electrons resting in invisible shells around atoms. These electrons are sensitive. They tremble easily, and when light enters their domain, it shakes them, like a hand brushing past a line of wind chimes. This shaking is nothing more than the electric field of the light tugging gently on the electrons. But each time an electron sways, it creates its own tiny flare of light, a soft echo of the original wave. These echoes blend with the main beam, forming a new combined rhythm, a rhythm that moves more slowly through the material. It's not that the photons themselves slow down. They still dart between atoms at their usual cosmic pace. What slows is the pattern they form together. Imagine a crowd in a stadium performing a wave. The wave travels quickly around the arena, but each person stays in their seat. No individual moves far or fast, yet the pattern sweeps around with elegance. Light moving through matter is just like that. The wave travels, but the individuals, electrons, barely move. This makes the whole process feel almost alive. Light enters a material, sways its electrons, waits for them to respond, gathers their echoes, and only then continues. These tiny delays add up, slowing the beam in a way that feels like watching someone pause to greet each person along a hallway. In everyday life, we rarely notice this dance. Light slows just a little in air, a bit more in water, far more in glass. But in certain environments, ones crafted with care and cooled to unimaginably low temperatures, the slowing becomes dramatic. In one celebrated experiment at Harvard, scientists guided a pulse of light into a cloud of atoms chilled almost to a standstill. The atoms' electronic shells became so responsive, so ready to echo, that the pulse of light crept forward at a human walking pace, 5 kilometers per hour. Light, the universe's swiftest traveller, slowed to something that could stroll beside you. Then something even stranger happened. By adjusting the properties of the atomic cloud, the scientists caused the pulse to halt entirely. Not destroyed, not dimmed, just stopped, caught in the whispering dance of electrons. And when they shifted the conditions again, the pulse continued its journey, picking up where it left off as though time inside the cloud had simply taken a long, quiet breath. This does not mean light itself becomes frozen in place. It means the pattern, the wavefront, become stored inside the atoms, waiting patiently to be released. The photons themselves are absorbed and re-emitted in a graceful relay, passing the message forward like runners in a race who share one baton. To appreciate the beauty of this without slipping into technical language, think of 3 different ways a wave can move. There is the way the shape of the wave moves, like a smooth ripple drifting across a still lake. There is the way the peaks of the wave move, like watching the crests of ripples in a pond after you drop in a stone. Some crests may appear to race ahead faster than the ripple itself. And there is the way true information moves, the moment when the wave first begins, the leading edge, the place where something genuinely new appears. In light, these 3 motions can differ. The ripple may drift gently, the peaks may jump forward quickly, but the true, meaningful part, the front, the message, is always steady, always respecting the universal rules. This is why slowing and stopping light does not break anything fundamental. It's the pattern that slows, not the message inside it. Somewhere in all of this, complexity lies a quiet reminder. Even something as reliable as light is shaped by the world it travels through. Whether it's the thin air of a mountaintop or the dense transparency of glass, light must negotiate with each electron it encounters. It bends, pauses, blends, and waits. And in that waiting, time itself is reshaped. For anyone standing nearby, watching a beam of light enter one of these special atomic clouds, the effect would look calm, almost peaceful. The beam would arrive, fade softly as the atom held it, then return with its original rhythm intact. But beneath that calm lies a slow dance of interactions, light lending time to matter, matter echoing back its gratitude, and the universe allowing a pulse of illumination to rest for a moment before continuing on its way. This tender exchange sets the stage for even stranger behaviour, moments when light seems to outrun itself or explore paths through time that we cannot easily imagine. But for now, it's enough to recognise that even light, the swiftest traveller we know, is shaped by the world's quiet structures. It reminds us that nothing moves alone. Everything is part of a dance. There is a moment in the story of light that feels almost like a magic trick. A soft, harmless experiment performed inside a quiet laboratory, yet one that leaves even seasoned physicists sitting back in their chairs, blinking slowly, wondering if they truly saw what they thought they saw. It happened at the turn of the century, inside a chamber filled with a thin cloud of cesium gas. Researchers sent a gentle pulse of light, a brief flicker, a momentary glow through this cloud, and watched its journey with great care. They expected the pulse to slow, of course. Matter always persuades light to dance a little more slowly. But then something unexpected happened. The pulse seemed to exit the cloud before it fully entered. Not the information inside the pulse, not the message it carried, but the bright crest, the shape, appeared at the far end early, as though it had leapt ahead of itself. For a brief moment, it gave the illusion that light had outrun light. Of course, nothing truly outruns itself. Nothing breaks the rule that information must travel steadily, without shortcuts, respecting the universal speed limit the cosmos has held since the first stars shone. But this strange moment is a reminder that waves, whether of light, sound, or anything else, can behave in ways that leave intuition far behind. To understand the illusion gently, imagine standing in a crowded stadium. One person raises their arms, then the next, then the next. A wave sweeps across thousands of people, racing around the arena faster than any single person moves. The wave can even leap forward if the crowd is prepared, if each person knows when to raise their arms based on a rhythm already felt, already expected. The wave appears fast, but the people remain where they are. In the cesium cloud, the atoms behave something like that stadium crowd. Their electrons sway in patterns shaped by the light entering them. They anticipate the flicker, responding not only to the crest itself, but to the leading hints of its rhythm. When the pulse arrives, the atoms immediately begin to emit their own tiny flashes. These echoes build the crest at the far side earlier than expected, not because the original light outran itself, but because the medium reconstructed the crest ahead of schedule. The pulse that exited was not the pulse that entered. It was a carefully assembled facsimile, pieced together by the atoms as they whispered to one another. It feels eerie, almost like watching the shadow of a runner stretch forward, reaching the finish line before the runner's feet touch it. But shadows do not carry information. They only mimic the outline. And so it is with the pulse, the true, meaningful part of a light signal, the leading edge, the place where something genuinely new begins, never outruns, the universal limit. It is steady, unwavering, as reliable as gravity itself. What leaps ahead is the crest, a decoration on the wave, an ornament shaped by the medium it passes through. The universe allows illusions, but not violations. To soften the idea even more, think of throwing a pebble into a pond. The moment the pebble touches the surface is the true beginning of the ripple, the part that carries information. But if the pond already has gentle waves rolling across it, your ripple may appear to reach certain points sooner or later depending on how it mixes with the pre-existing patterns. This does not change the moment the pebble fell, it only changes how the shapes combine. Light experiences the same blending inside matter. The cesium atoms have resonances, preferred ways of swaying, that make them respond very strongly to certain frequencies. When the pulse arrives, the atoms do not simply obey it, they anticipate it, reconstruct it, and sometimes even pull its pattern ahead of schedule. The mind rebels at this at first because we often imagine light as a single solid entity, a bullet of brightness moving from point A to point B. But light in truth is a wave, a pattern that can be broken, remade, echoed, rearranged. And when waves pass through unusual environments, their behaviour can appear to bend the rules, even though the underlying structure remains intact. This experiment is a gentle reminder that nature often hides complexities beneath familiar appearances. Just as wind can push ocean waves faster than the water beneath them moves, or just as a crowd can generate ripples that seem independent of any individual, light inside certain materials can create the illusion of speed beyond its own limit. But the limit remains. The universe keeps its promise. There is something soothing in that. Even when the cosmos behaves in ways that seem contradictory, it quietly ensures that the foundations hold firm. Information does not rush ahead of itself. Cause does not trip over effect. Moments do not reach out into the future without touching the present first. The rules are steady, even when the surface dances. Still, there is a kind of dreamlike beauty in the idea of a pulse appearing early, as though the future briefly brushed against the present. It makes the world feel slightly more mysterious, slightly more alive. It hints that light, a thing we think we understand so well, may still hide soft surprises in its folds. When the researchers repeated the experiment, the same strange illusion appeared. The pulse arrived early, yet nothing meaningful had been transmitted faster than the universe allows. It was a performance, a delicate choreography between light and matter, a dance that tricked the eye while leaving the deeper laws untouched. Moments like this remind us how subtle the world truly is. Even the simplest thing, a flicker of light, can reveal structures that feel almost like riddles whispered by the universe, and, although we eventually understand the mechanism, the sense of wonder stays. Light does not outrun itself, but in certain environments it can appear to drift ahead like a ghost of its own future, carved out of echoes the medium has woven for it. A reminder that the world beneath its calm surface still knows how to surprise us. If you've ever stood beside a quiet pond and tossed in two small pebbles, you've seen a simple but beautiful sight. Two sets of ripples expanding outward, meeting each other, crossing, weaving into gentle patterns. In one place the ripples lift each other upward, In another, they cancel softly, leaving a still patch. This familiar dance, interference, is one of the first hints children get that waves can combine, undo, or enhance each other. Now imagine something far stranger. Imagine that instead of two pebbles tossed into the same place, the pond receives one pebble now, and another pebble just a moment later. Their ripples meet not because they were created side by side in space, but because they overlap in time. Not ripples in a pond, ripples in light. That is the spirit of a remarkable experiment performed in 2023. One that revealed a piece of nature quiet enough to miss, and strange enough to stay with you long after hearing about it. An experiment where scientists created slits in time. To understand why this is so surprising, it helps to recall a familiar idea from school, the double slit experiment. In that setup, light shines through two narrow openings in a barrier. The two beams spread out and overlap, forming an interference pattern on a screen, a series of bright and dark stripes made from the way the waves meet. It's a simple demonstration, almost gentle, that light has a wave-like nature. But what those scientists achieved in 2023 is not a double slit in space. It's a double slit in time. Instead of carving openings in a physical barrier, they created openings in the reflectiveness of a material, moments where a thin layer behaves like a mirror, separated by only a faint breath of time. When a laser pulse passes through during one of these brief mirror-like instants, part of the light is reflected. If the mirror appears twice, two slits in time, something magical begins to happen. The reflections created at these two moments produce ripples that overlap not in space but in frequency. A ripple in frequency is like a ripple in colour. Some wavelengths brighten, others disappear, leaving a comb-like pattern, bright, dark, painted across the spectrum. It's an interference pattern just as real as the one from a spatial double slit, but woven into the colours themselves. To make this happen, the researchers used a material called indium tin oxide, the same substance that makes touchscreens conductive. Under certain conditions, it can transform from transparent to reflective incredibly quickly, within a fraction of a trillionth of a second. For the briefest instant, it becomes a mirror. For the next instant, it stops. Then it becomes a mirror again. Two flashes of mirror, two openings in time, and light responds to those instants just as it would respond to two slits standing side by side in space. The gentle analogy is this. In space, two slits divide the beam into two paths. In time, two slits divide the beam into two moments. Instead of the beam choosing between left and right, it chooses between earlier and later. And when the earlier and later reflections overlap, the ripples cross in the dimension of colour, forming a pattern that tells us time itself can act like a medium, shaping the wave. To picture this softly, imagine a vertical diagram with time running upward. Place a small horizontal bar on the line. That bar represents the first instant the mirror exists. A little above it, another bar, the second instant. When a photon passes through this region, it interacts with both bars with two slightly different versions of itself, one arriving just before, one arriving just after. These two versions overlap in the space of frequency, not position, and the way they cross, where they reinforce, where they cancel, produces a delicate comb of bright and dim colours. In everyday terms, it's as if light briefly meets its own past and its own near future, comparing the two impressions and leaving behind a fingerprint of their difference. Some people hear this and imagine light travelling backward or forward through time. But the more careful way to put it is this. Light explores multiple possible routes through space-time before settling into the one we measure. Not paths between different places, but paths between different instants. Light is sensitive not only to where things are, but also to when they change. It responds to time the way ripples respond to stones dropped at moments separated by a breath. Nothing supernatural occurs. No messages are sent from the future. No paradoxes bloom. It is simply the wave nature of light, extended gracefully into the time dimension, revealing that what we experience as a sequence of moments is part of a larger fabric, where spacing in time can shape a beam, just as spacing in space once did. One way to picture this is to imagine standing in a quiet field watching fireflies. If two fireflies flash at slightly different times, you still perceive both glimmers. Now imagine each flash sending a ripple through the air, tiny waves of brightness spreading outward. Those waves overlap, not because they come from different places, but because they come from different moments. Interference does not care whether the slits are carved in wood or carved in time, it only cares about the rhythm. This experiment also reveals a subtler truth. Inside the mathematics of light, paths are not single lines drawn solidly from A to B. Instead, light quietly considers many possible routes, some faster, some slower, some looping through, unexpected curves of space-time. Most of these possibilities vanish without leaving a trace, but under the right conditions, like two mirror-like instants in a row, we can catch a glimpse of these hidden pathways, like seeing a fish break the surface of a lake for only a second before disappearing again. What we witness in the time-slit experiment is not the fish, not the full path, but the ripple it leaves behind. Moments like this invite a quiet wonder. They remind us that the boundaries we draw between now and not now, between before and after, may be softer than we imagined. They remind us that time is not a smooth, unbroken stream, but a fabric that can be probed, tapped, and made to vibrate. A fabric through which light weaves paths that stretch beyond our ordinary intuition. And for a brief moment in that laboratory, light touched two slices of time and revealed how finely the universe is stitched. If you've ever watched sunlight spill through a window, slipping over the curve of a table or glinting across a glass of water, you've seen something beautiful without realizing you were witnessing a quiet miracle. Light never travels carelessly. It never chooses its path randomly. It always follows a rule so soft and elegant that it looks almost like intuition rather than physics. The rule is this: light always chooses the path that takes the least overall time, not the shortest distance, not the simplest line, the least time. This idea, first uncovered centuries ago, is almost tender in its simplicity. If you place a mirror between yourself and a candle, the reflection you see is created by light that has chosen, from infinite possible angles, the angle that allows it to reach your eye in the least amount of time. The reflection feels instant, but behind it lies a delicate negotiation. The mind naturally imagines light as a traveller that knows where to go, choosing the fastest route the way you might pick the quickest lane at the grocery store. But that is only a metaphor, and a fragile one. Light does not plan, it does not think. What it does is far stranger and far more beautiful. To understand it gently, imagine walking into a forest where the ground is uneven. You want to cross from one side to the other, and you want to do it quickly. You could take a straight line, but that path might lead over steep hills. You could take a longer detour that winds through a valley, which might be faster overall. Without consciously thinking, you scan the forest, sense the easiest route, and follow it. Light behaves like this instinctively, except it does not scan. Instead, it explores. This exploration does not happen as a physical event you can photograph. It happens in the mathematics beneath the surface of reality. But a soft and more human way to imagine it is to picture lightning. When it forms inside a cloud, lightning does not travel directly from point A to point B. Instead, it tests many branching paths at once. Some branches fail, one succeeds, and once a path is chosen, the full bolt follows. Light does something similar, but silently, instantly, everywhere. Even a single beam, passing from air into water, tries out all possible angles, and the angle that would take the least time becomes the one that the beam actually follows. It is an elegant choreography where the universe appears to run through every possibility, keeping only the one that fits its rule. This might feel like a trick of language, but experiments show us that it's more than metaphor. Light behaves as if it quietly touches all paths before choosing one, not exploring in the sense of crawling around, but exploring in the sense of forming a pattern, a soft collection of possibilities, each with a weight. Wave patterns allow these possibilities to blend, cancel, and reinforce one another until only the true, real path remains. Now imagine what happens when time itself begins to wobble, when mirrors turn on and off in femtoseconds, when materials shift their nature in flashes shorter than a heartbeat of an atom. Suddenly, the possible paths of light begin to include not just different places but different moments, and light must choose, as always, the path that resolves into the least overall time. Except now, the meaning of time in that equation becomes harder to pin down. In some diagrams, physicists draw soft conceptual sketches, not actual blueprints. The possible paths of light curve and loop. Some lean forward into the future before bending back. Some lean backward momentarily before resuming their forward flow. These are not real balls of light rolling backward in time. They are faint possibilities that cancel or reinforce until the final path emerges, the one we actually observe. Think of a violinist drawing a bow across a string. The bow touches many fibres at once, but only the final vibration remains, the one that the structure of the instrument selects. Light does something similar with time. It touches many possible moments, but only the one consistent with the least time rule survives. This helps us understand why the time-slit experiment produces patterns that seem to mix earlier and later versions of a photon. Light is not moving backward in time. It is simply allowing its wave nature to test multiple temporal possibilities until the final path, the one that satisfies its rule, emerges. The least time principle is sometimes called the universe's great compromise. Light does not insist on taking the straightest path, it takes the most efficient one. And when the environment changes, when materials flicker, when gravity curves space, when time stretches or contracts, light adjusts without hesitation. Imagine standing at the edge of a frozen lake, looking across at a distant lantern. Light from the lantern bends across ripples in the air, skims through pockets of warm and cool layers, and sometimes seems to shimmer like a thought drifting in and out of focus. This shimmer is the result of light negotiating countless micropaths, each one affected by the tiniest fluctuations of temperature and density. You do not see the negotiation, only the final, shimmering result. In the same spirit, when light travels through regions where time is sliced into brief reflective instants, or where gravity curves space into deep basins, or where materials pulse between transparency and reflection, it considers many routes through space-time. Most fade, one remains. This idea that light feels out the future does not mean that the universe cheats its own rules. Rather, it means that time, like space, is woven into every path. Light's behaviour emerges from the entire structure, not just from what lies directly ahead. To the human mind, which experiences moments in sequence, this can feel unsettling. We expect causes to precede effects, paths to be chosen based on present conditions alone. But light does not share our limitations. It follows the full geometry of space-time, not the narrow slice we experience. And so, when we study these strange experiments, slits in time, pulses that appear early, paths that seem to bend around moments, we're not witnessing law-breaking. We're witnessing the deeper order beneath those laws. An order where time is not a river flowing outward from the past, but a dimension joined with space in a single tapestry, explored by waves that sense the entire cloth. What emerges is gentle, almost serene. Light always settles on the path that fits the shape of space-time itself, and sometimes that shape allows hints of the future to leave faint whispers in the present. There is a moment in quantum physics that feels less like a scientific discovery and more like a whisper between distant stars. Two tiny particles, born together in the same event, can drift apart across unimaginable distances, separated by planets, light years, or the quiet vacuum between galaxies. And yet, when you measure one, the other responds instantly, as if the universe forgot to put space between them. This is quantum entanglement, and it sits at the edge of what our minds find comfortable. Not because it breaks the speed of light, it does not, but because it bends our sense of before, after, and somewhere else. To feel this gently, imagine two coins forged from the same shimmering metal, cast in the same moment by a quiet, ancient mint. The coins are tossed into opposite corners of a wide, silent hall. You pick up one coin, cover it with your hands, and flip it. When you reveal it, let's say it lands on heads, the other coin, no matter how far across the hall, will land on tails the instant you look at it. Not because one coin sends a signal to the other, not because they have secret markings telling them what to do, but because they are not really two stories, they are one. Entanglement weaves a single tale across two distant places. To understand why this feels so bewildering, it helps to soften one common misunderstanding. Many people imagine that each particle secretly carries a set of instructions. That particle A, for example, carries a hidden note saying, "If anyone measures me pointing north, I will spin upward. If they measure me pointing east, I will spin downward." In this view, particle B carries the complementary note so that everything stays consistent. This is the classical picture, the one that early thinkers hoped would save our intuition. But reality refused to cooperate. Experiments were designed to test this hidden instruction idea, and they used something akin to a game of comparing coin flips. The rules were simple. Measure each particle in different directions and record how often the results match or mismatch. If the particles carried hidden instructions, certain patterns would appear, patterns that could be predicted using ordinary statistics. But when the experiments were performed, the results were not merely unusual, they were impossible if hidden instructions existed. Instead of matching in the classical way, entangled particles match in a deeper, quieter way. Their outcomes correlate with a kind of softness and precision that no local explanation can imitate. The match rate drifts toward a very specific value, not the one classical physics would demand, but one that only quantum mechanics predicts. A gentle metaphor can help. Imagine trying to choreograph a dance across two distant stages. The dancers cannot speak to each other. They cannot send signals. They cannot plan routines in advance. And yet every time the curtain rises, their movements correspond with a harmony no classical choreography could produce. Not perfectly synced, but synced in a quantum way. Subtle, statistical, unmistakable. This is what entangled particles do. They do not pass messages. They do not cheat the rules. They simply share one underlying story, no matter how far apart they travel. To appreciate this without slipping into technical language, imagine again the tall stack of moments, the layers of space-time that stretch from past to future. Entangled particles are like two thin threads woven through this stack in a single motion. You may pull gently on one thread at the top and the other responds below, not because a signal was sent, but because the two threads were never truly separate. They are part of the same weave. You might ask, does this allow faster than light communication? The soothing answer is no. The results of each measurement still appear random to the person watching. One particle may show up or down with equal likelihood. It is only when the two distant observers compare notes later, long after light has had time to travel between them, that the remarkable correlation becomes clear. Until then, each observer sees only chance, not a message. Entanglement does not let us whisper messages across galaxies. It lets the universe whisper patterns across galaxies. Another gentle metaphor helps here. Imagine two spinning tops launched at the same moment, but with a twist. Their motions are entangled. If you look at one top alone, its spin looks random. But if you film both and later play the footage side by side, a hidden choreography appears. Each tilt of one top reveals the complementary tilt in the other. You could not have predicted this from watching only one top, just as you cannot predict the quantum outcome of a single particle alone. But when you place them together, you see that they are two halves of one movement. This is the essence of entanglement. Not communication, not causation, not spooky messages crossing the universe, just a shared story. And that shared story bends our idea of time. If two particles can correlate instantly, even across enormous distances, then perhaps now is not the same everywhere. Perhaps the universe doesn't slice moments the way we do. Perhaps the division between before and after is more like a line drawn in the sand, easy to disturb, easy to reinterpret, rather than a rigid frame that binds reality in place. You might picture entanglement as a soft bridge between two distant shores, not a bridge made of matter or energy or signals, but a bridge made of relationship, a connection that remains even when the participants drift far apart. And when you observe one side of the bridge, the other side responds, not because it receives the message, but because the bridge itself shifts. This is why entanglement is so often described as non-local. It is not local the way a whisper is local, not local the way a knock on a door is local. It is local in a deeper way, local to the space-time structure that joins both particles in a single pattern. And once you sense this softness, something becomes clear. Entanglement is not about breaking the rules of time. It is about showing that time and causality may be softer than we imagined. Imagine holding a single photon, a tiny bead of light in the palm of your hand. You open your hand and it begins its journey forward, gliding through space as softly as a drifting thought. Ahead of it sits a simple device made of mirrors and glass plates. Quiet, unassuming, smaller than a shoebox. Nothing about it looks strange. Yet this little setup contains one of the most unsettling ideas in all of physics, the possibility that the future can influence what the past must have been. Not in a dramatic sci-fi way, not with paradoxes, messages, or rewriting history, but gently, like a whisper shaping a memory just as it forms. This is the essence of the delayed choice experiment, a variation of a simple device called the Mach-Zehnder interferometer. Though the name may sound complicated, the idea is gentle if we take our time. Picture the device as a kind of maze made of two half mirrors and two ordinary mirrors. When the first half mirror stands in the photon's way, it behaves like a crossroads that sends part of the wave of light upward and part of it sideways. If the photon behaved like a wave, it would quietly explore both paths at once, drifting through the maze in a soft split state. Then the two paths meet again. And this is where the universe must make a choice. If the second half mirror is in place, the two paths reunite. The wave-like halves merge, comparing their rhythms. Where the rhythms align, brightness appears. Where they cancel, darkness appears. The photon ends up in one detector every time, in a pattern that tells a clear story. I was a wave, I took both paths. But if the second half mirror is removed, the paths no longer reunite. Instead, the photon travels one way or the other, arriving randomly at one detector or the other. The pattern now tells a different story. I was a particle, I took only one path. Both of these behaviours, wave-like and particle-like, have been tested and confirmed countless times. But the trouble begins when we delay the decision. What if we choose whether or not to insert the second half mirror after the photon has passed the first one, after it has already chosen its path? If we insert the second mirror at the last possible instant, The photon behaves as if it had always been a wave, calmly taking both paths and interfering with itself. But if we leave the mirror out, the photon behaves as if it had always been a particle taking just one, as if the future choice reached backward and settled the earlier story. This is the heart of the delayed choice experiment, and it gently challenges the way we imagine time flowing. We like to believe that cause happens before effect, that choices ripple forward, not backward. Yet at this tiny scale, the universe does not seem to follow that rule tightly. Instead, it behaves as though the photon's past remains uncommitted, soft, flexible, until the moment we perform the final measurement. Physics does not claim that the photon literally travels backward in time. Nothing supernatural occurs. Instead, the universe seems to work in loops of possibility. Before the measurement, the photon does not choose a path. It does not decide. It exists in a quiet collection of potential stories. The measurement does not change the past. It selects which past was relevant. Picture a soft sketchbook filled with faint pencil outlines of possible drawings. Only when the final stroke is added does one drawing come into focus. The other sketches fade, not because they were erased, but because they never matured into reality. The photon's history blooms only when the entire process is complete. This becomes even more dreamlike when we consider modern experiments that scramble the order of events. In some quantum devices, one operation is applied before another, yet from another perspective, the second operation comes first. The two processes braid together in a way that refuses to fit into a single fixed timeline. Physicists call this indefinite causal order, but a softer name might be causal fog, a place where before and after lose their rigidity. A gentle way to imagine this is to picture two painters standing on opposite sides of a canvas, each adding strokes without seeing the other's work. When the painting is finished, the strokes make sense. They fit together, harmonise, form a coherent picture. But if you try to decide which painter added their strokes first, the answer becomes slippery. The order doesn't matter. The final image is defined by the whole dance, not by a strict sequence. Quantum events behave like that. They create outcomes that are shaped by the entire experimental setup, not by a simple line of cause followed by effect. And this calls into question the story we tell ourselves about how time flows. We tend to imagine time as a river running from past to future, carrying us with it. But experiments like these hint at a different metaphor. Time might be a tapestry, woven in loops, where moments are connected by relationships rather than by strict order. In this view, the universe is not rewriting history. It is revealing which threads belong to the final weave only when the full context is present. A photon's path is like a note in a chord, meaningful only when heard together with the others. The delayed choice experiment invites us to soften our assumptions, not to abandon causality, but to understand that the deep structure of the universe may not obey the same tidy sequence our daily lives depend on. At the scale of photons, electrons, and atoms, the story of an event includes not just what happened before it, but what happened after it. The universe's accounting sheet is not chronological, it is holistic. This idea does not threaten the macroscopic world we know. Your coffee still cools from hot to warm, never the other way around. You still grow older each day. The arrow of time, born from entropy and disorder, carries our world forward with a reassuring steadiness. But in the smallest corners of reality, the arrow frays, the boundaries soften, cause and effect swirl gently around one another. And if we listen closely, these experiments whisper a message that is both humbling and comforting. The universe is not a rigid machine but a conversation, one in which even the future has a quiet voice.